Hello, everyone. Today I'll be giving a talk that I gave recently at FabTech in Chicago, Illinois, at McCormick Place. It's from a session that was dedicated to tube and pipe welding. What's happened today, basics, testing, and new innovations workshop. So my talk was called Improving HF Tube Welding System Performance Using SMC Impeder Cores. My name is Robert Goldstein. I'm a fellow of ASM International and currently the Executive Director of Strategic Planning and Product Development at Fluxtrol. And I worked on a lot of portions of this presentation with Sean Meiskens, a Senior Research Engineer at Fluxtrol. So this will be a little bit of a non-traditional presentation. I'm going to start out with why this talk matters and really why you should listen. Then we'll get into some of the more technical details, such as how induction tube welding actually works, impeder benefits and material selection, some case studies besides the one we'll start with, and then soft magnetic composite impeder offline validation. It's a key feature to help de-risk the development process and make sure that we don't waste your valuable meal time. And then we'll kind of wrap everything back up at the end. So we're going to start with the case story. So this case story was done at Princeton Company, GmbH Stahlrohr. Okay, this was actually organized by Technical University of Chemnitz, a small impeder manufacturer called TW Tools, and Princeton Stahlrohr, and was funded by the German government through the Imagine project. So for this installation, we have a 400 kilohertz power supply, 50 to 150 kilowatts, 15 millimeter OD steel tube, 1.2 millimeter wall thickness, and the customer was using 8.5 to 9 millimeter OD impeders. When two impeders were tested, one impeder was a 9 millimeter ferrite impeder, and the other one was 8.5 millimeter Fluxtrol 50 impeder. Each was done at a 77 meter per minute line speed. And you can see with the ferrite impeder, the 58 kilowatts, that's a pretty good number. But then when they switched to the Fluxtrol, the power demand dropped to only 33 kilowatts. Besides that, the reason why the customer was open to test on this line is typically the ferrite impeders were lasting only about 4 hours. So that means if you were going to do a longer run, you'd have to change that impeder about twice a shift. When they switched to the Fluxtrol 50 impeders, they were experiencing greater than 20 hours of impeder life with little to no sign of wear. So the primary goal of that savings in Europe was energy savings and carbon reduction. And they prevent 87 tons of carbon dioxide per year if this were implemented and averaged over a 5,000 hour production run. The savings from energy, now this is calculated based on US rates at 8 cents a kilowatt hour. In Germany, they're 2 to 4 times as much depending on where you are. It was 10,000 US dollars, so that would have been $20,000 to $40,000 in savings to the customer. These are all great things, but they're only part of the story. If we look at what benefits a mill would get from this, one of the concerns that we have out there is SMCs are known to be much more expensive than ferrites. So this just kind of calculates what would happen if you had 5,000 hours a year production. The impeder life was 4 hours versus 20 hours. And let's just say the core cost was $200 instead of $5. That lead to an impeder cost on the order of $55 here versus about $275 here. But your changeovers a year would decline from 1,250 to 250. That would mean actually the cost was neutral. So even though the core is 40 times as much, actually how much you're going to spend on your impeder consumables would be the same for your line. Now we can start to look at the savings. So if you look at the energy, we already documented that at 8 cents a kilowatt hour, you save about 10,000 US dollars. With rates closer to 20 cents, 25 cents in Europe, that's 2.5, 3 times as much. But here's the real savings. We've been doing research and we've talked to a lot of people in the field. And generally, when you're running these lines, it's somewhere between $10 and $60 a minute is the value you create by running that tube mill. Generally, it takes about 30 minutes. When an impeder fails, until you install the new impeder, you have to take the old one out, cut out some steel, get everything back together. And if you're having to do that 1,250 times a year versus 250 times a year, the cost of that changeover time is from $375,000 on the low end to $2.25 million on the high end. The 250 hour number, 250 changeover number, that's $75,000 to $450,000. So 300,000 to 1.8 million in cost reduction. If you look also at the scrap, and depending on what type of product you're doing, what type of steel, this steel is fairly simple, so about $1 a pound is a kind of our estimate. If it takes between 1 and 5 minutes from the time you get, okay, I've got my new impeder in, till that line is running and you verify that your weld is good, that's generally about 1 to 5 minutes. So that means you scrap between 70 and 350 pounds of steel during that period. If you multiply that by the number of changeovers a year you have, it leads to your scrap cost, $86,000 to over $400,000 a year from 1,250 changeovers. But we go to 250 changeovers, it drops substantially, that number. This leads to a net annual savings from that change of $380,000 to about 2.2 million. One can understand when there is no capital investment required to get that savings, and really it's cost neutral on your spend from purchasing, we can see that really these cores are probably too inexpensive compared to what savings you're actually getting. So people look at that number and say, well, okay, cherry pick a case, you're just kind of making up numbers. Well, this was a case study that was done in Serbia by a Romanian group. We had no involvement in these trials other than they bought Fluxtrol A to make these impeders from us. That was our only involvement. So this is a little bit larger tube, 21 to 27 millimeter OD steel tube, 2.6 millimeter wall thickness. They used 13 millimeter OD impeders, and they tested at a variety of speeds between 10 and 60 meters a minute. And they documented between 30 and 50% energy savings when using Fluxtrol A for the same line speed. And you can see the two graphs that they generated. One was with the TDK ferrite, which is the market leader, and the other one was Fluxtrol A. And you can see that kilowatt hours per ton drop dramatically. The other thing that we found in their publications, they ran a series of publications that were published in peer-reviewed journals. Again, they came up with this number: about 5 times those impeders were lasting longer in production. So these were produced in a lower cost country. Again, this was published in a journal. They tested not just ferrites from TDK, they tested a local ferrite, which was lower quality. You can see the big difference in kilowatt hours per ton. They also compared this to standard data available from Japan on an amorphous laminate special hybrid impeder, which TDK ferrite was better than as well. Also noticed that these impeders were twice as long, which generally using a longer impeder helps to improve the efficiency. And then you can see the Fluxtrol A, and almost half the kilowatt hours per ton, same speed. And even they only used a 6-inch roughly heater instead of an 8. They used a shorter. All of these things say that this should take more power, but it's substantially less than the TDK ferrite. And the key thing is they actually calculated their production savings. This was published in 2014. They were documenting about $350,000 a year from making this change from the TDK ferrite impeder to the Fluxtrol A impeder core. So, means we're not so far out there. Let's try and understand a little bit why this might be happening. So the induction tube welding process, this is something that's been around for a long time. The first patents were in the 40s, and it's been known to be in production since sometime in the 1950s. So kind of what happens, you start with a coil of steel, you roll that strip out, you start to roll it and form it into a tube, and then it goes through the induction coil, which generates high frequency currents along the edges, which are then squeezed together and forming a weld, and later typically you'll remove the external bead. So if we look at this graph, it's kind of a little bit confusing, but a tube that's being welded is an open profile, the area under the induction coil. So from the induction coil, the tube acts as a secondary for that primary, which is the induction coil. The currents try to flow around the body in the opposite direction as they flow in the coil. However, when they hit the open profile, they're not able to finish their loop. And the law of physics says that all currents need to be closed loop. So at this point, the currents start to diverge, right? And they have three choices of which way to go. One way is to go down the edge of the weld seam to the welding point and then return back here. This is the most desirable pattern. The other way is to go backwards along the edge of the seam and then return along the tube body and then head back to the other side. This is also very beneficial as it heats the edges of the weld. Not quite as beneficial because you still get some additional loss from it traveling around the outside of the tube. And the third way it potentially can go is when it turns here, it can go back on the inside and flow along the ID of the impeder. So this is what you want to avoid. So what's happening in the market? What's changed? Why now? There's a wide availability of higher, more efficient power supplies at a choice of frequency. So we have improved material handling systems. The technology for moving and forming and cutting metal has gotten better. In association with that, the faster things start to move, you need improvements in your process control and monitoring. And there's a lot more data that we're collecting on our modern mills, and a lot more control that we have, and a lot more understanding we get of what is going on within our production cells. Industry 4.0 changes, trends are really starting to modernize the tube line. The improved material cutting, right? If you're processing more material, most of these are cut to length. Some stuff's coiled, but you've got to be able to cut to length, and the ability to actually cut faster, heavier gauge that's moving faster, that's really been a major source of improvement and modernization. It's really started to move things farther towards everything is capable of doing more. And now we're starting to run back into this limit that the performance of many small tube installations is really limited now by the impeder, which is really the least expensive part of the whole thing. So what is that impeder? It's an assembly that contains a soft magnetic material that impedes the current flow on the inside of the pipe. So its role is to stop the current from going to where you don't want it to go. It's typically manufactured historically using ferrite materials, and it's fixtured within the forming tube. So if we look at a through flow impeder trial, and this is one that we conducted in Canada back in 2019. So a trial was run replacing a ferrite impeder with the Fluxtrol 75 impeder. So the customer was experiencing very short lifetime of ferrites, and they were not able to meet production targets. So we set up a line for approximately 20 minutes, and we ran that line at the same speed for both impeders, and the electrical parameters were recorded. And the induction system was set up the same in both cases. Only the impeders changed, because people familiar with induction will tell you it matters what the angle of the weld V is. It matters where the location of the induction coil is, where the impeder. We literally took one impeder off, put the other impeder in. All the other things held the same. We published a lot of details about this in some papers back in 2019, right before the pandemic. So you can see there the mill actually running with the Fluxtrol 75 impeder in there. So here are the results of the trial. So we measured the current at the inverter and multiplied it by the turns ratio in the transformer. So with the Fluxtrol 75 impeder, it took 5,000 ampere turns and the power supply read 200 kilowatts at 82 meters a minute. With the ferrite impeder, it took 7,300 ampere turns, 325 kilowatts, 82 meters a minute. Now, they were not able to turn the line up any faster with the ferrite impeder. With the Fluxtrol impeder, they were able to go up to the rated speed of the line, 96 meters a minute. It only took 220 kilowatts and 5,400 ampere turns. So if we look at the same power at the same speed, over 30% lower current and almost 40% lower power for the same production speed. This was a trial. The impeder didn't fail, but it was just a planned trial. This is how much material we're going to produce. And each were done for 20 minutes. So when we look at that, this is data from the machine. Okay, where did all the current go? All right, and how come there's so much difference in power when the temperature of the weld is the same? We looked at using computer modeling. So we used a process where we did two types of modeling. One's 2D and one's 3D. So this tube was 19 millimeter with a 3 millimeter wall thickness. There was a 2-degree weld V angle. The coil here we just show conceptually as a single turn. How many turns you need is just really for matching to the power supply. It doesn't really affect our modeling results much. We have a 24 millimeter ID on the coil and 41 millimeters length. The length and the ID, those are important to the model. And the distance from the end of the coil to the welding point was about 64 millimeters. The impeder we used was 9 millimeter in OD and 230 millimeters in length. Here is the resulting magnetic flux density distributions in the impeder core. If we look below, ferrites at room temperature, typically used for welding, have a saturation flux density 0.45 to 0.5 Tesla. We can see here that this ferrite is well above the saturation flux density. And what happens is the natural distribution widens way out. Whereas with the Fluxtrol 75 impeder, the distribution of flux is much tighter and much more natural for what it should be in this type of tube. So this is a much more favorable distribution because we're below our saturation flux density in the core. So where did all that current go? Well, it flowed on the ID of the tube. So because that ferrite was in saturation, it's no longer able to do its fundamental job, which was to impede the current on the ID of the tube. So once you take away the blocker, now the current flows along the outside of the tube and it flows on the inside. If you look at the Fluxtrol 75, you don't see this current on the inside. So fundamentally, this extra current on the inside, well, that means that I have to have more current on the outside because all currents have to be closed loop and continuous. It means I need more currents from the coil. Also means I need more current from the power supply. So all of these things compound, and really the problem is we've got all this extra current here. So where did the extra 50% of current go? It's right here. We look at the energy savings from this application. Now this was a lot more power than the previous one that we showed. So we were using 100 kilowatts less power and running the line 20% faster. That's 45% lower kilowatt hour per ton of tubing produced. If you use the same assumptions as the previous case, we represent 437 tons of carbon dioxide annually and save $50,000 in electricity costs. When we run at a higher line speed, we're preventing 480 tons of carbon dioxide and saving $55,000. In Europe, that number would be about triple. Now, for the same volume of product produced, we'd make the same number of tons of steel in 730 less hours. If you decide to continue producing steel during that time, your opportunity cost is about $1.35 million annually. And that's based on a 31 a minute line cost. If it were more like $60 a minute, that's $2.7 million. That's what you're giving up by not making the change and turning up your line to what it's capable of doing. One way to think about this is essentially this represents your induction coil. It's the primary of a transformer. Your secondary of the transformer is the tube. And if we think about it, you have three parallel paths. The parallel path one is the weld V before the coil. That's kind of that preheating loop we talked about. The other parallel path is the ID of the tube. And the third path is the weld V after the coil. This is really where we want it to go. We want it to go towards the weld V. This is our desirable path. Really, what the impeder does is it changes this inductance component. We work in induction welding, right? Called induction heating. Why is that? Inductance is the imaginary component. Resistance is the real component. And the induction is actually bigger than the resistance. So the current is going to the path of least inductance, not actually the path of least resistance, because the weld V is much higher resistance and the weld V edge are much higher resistance than on the ID. But we prevent it from going there with raising the inductance. How we do that is by the cross-section of area of our core and the magnetic permeability. That product is directly proportional inductance for the part ID path. That's why if you put a bigger impeder inside a tube, you will get more efficiency, right? Up until a certain point when you're at your threshold efficiency, but you get more efficiency because you've raised that inductance to that path, so you're driving more of the current towards the desirable path and less is going on the undesirable path. So what are the properties that we can use for a magnetic core for an impeder? Traditionally, manganese zinc ferrites have been used, and these look fantastic. As on the previous slide, I told you the product of magnetic permeability and cross-sectional area. That defines what the magnetic size of that core is and how much inductance that's contributing to the system. That's preventing that current from flowing around the ID of that tube. So these look fantastic. These permeabilities are in the thousands. Why would we want to use these soft magnetic composites that have permeability, closer to 100? Well, these have permeabilities of thousands, but only at saturation flux densities around 0.4. These have permeabilities of hundreds, but they have permeabilities of hundreds in the Tesla range, right? As we go here, better permeability this way, better this way. But really what we worry about is a better combination under the operating parameters. We can break it down quite simply. When is a ferrite the best choice for material and when's an SMC the best choice for material? It really depends on what flux density you're at. If you're below saturation, ferrites have much higher permeability. So for the same cross section, in this range, the ferrites might be 20 times better around here, or 10 times better here. But over here, the SMC is 50 times better. So it all depends on where you're operating. If you look at this ratio, that product of B and area, so that flux, how much flux it's carrying. If we look at the ferrites, over here, we're 50 times better, but the minute you hit here, now we're 20 to 50 times better. And it's important to keep in mind that these values all should be compared to air, which is kind of the empty space or the plastic tube is essentially equal to air, or the hole in the middle of the water. These are relative. So while this may be 50 times better, they're not 50 times better because already you're in the point of diminishing returns. The SMC material is already 100 times better than air. So it's already quite large. But over here, the ferrite is only 2 times better than air. Meanwhile, the SMC remains 100 times. So it's all relative, but this is why we're seeing such dramatic benefits in the ability to stop that internal current and degrade the performance of the system. So let's look at another case story here. This is for a return flow ampere. Unfortunately, due to confidentiality, I can't give all the details on this one like we've given on some of the other cases, but I think it presents a common problem and it gives enough information where you can visualize how this would really help your line. In this impeder, inside of the ID of the impeder core, there's a brass tube. In some cases, there's like a steel tow rod, but there's an electrically conductive component that's inside of the ID of the impeder core. And inside of this brass tube, then there is a steel rod. So there's very little space available for the impeder core. So instead of being able to fill that whole space, remember we talked about flux density times area, now most of the area is filled up inside of this core with conductive components. So the main failure mode of the impeder core was mechanical. It was rubbing on the tube because to get enough tube where the line could run, they had to run really close to the ID of the welded tube. Right. They looked at 2 different SMC cores. One that fit in the same casing as the current ferrite impeders, and originally we were looking at one that fit in 1 millimeter smaller casing than the ferrite impeders. Even a millimeter is a lot of real estate in there. And so we made all these calculations for this case without a tube in place, and only the induction coil and the impeder elements. If you look what it takes to drive that flux through the core, because the heating is proportional to the flux density squared that passes through the inside of that tube. You can see at low fields, the SMC cores require more current than the ferrites, but not incredibly dramatic difference between 80, 100, 120 or something like that. So 50% more. Once we get to 0.5 Tesla, now the SMC cores need 200 amps, but the ferrites need over 2,000 amps. Okay, power is I squared R. That's 100 times more losses than that coil. So you see quickly as you go up this slope, things degrade really quickly. Meanwhile, the Fluxtrol cores, they keep chugging along. So when we actually went to production, sometimes you don't get all the details. It turns out we were actually comparing our cores to impeder that they wanted to use its ferrite, but they couldn't get to work. So when they actually put our core in, it was 3 millimeters smaller diameter, 2 millimeters smaller impeder diameter than the current production impeder. So we shrunk that substantially. And keep in mind, there's a big hole in the middle of this, so there isn't much space for that impeder. And we still showed 20% energy savings. And tons more real estate, so the tube was no longer riding on the impeder. There was actually a significant gap, so they weren't going to wear out like they were. How we've started thinking about this is we've defined it as a region of high process efficiency. So if the impeder can carry the majority of the magnetic load of the ID path, the system's running near the maximum theoretical efficiency. So more or less all the current is running on the tube edges, the inner tube edges, which is where you want it. So we're calling this our region of high process efficiency. The difference between the Fluxtrols and the ferrites, or the permeability between 100 and 1,000, is much, much less than the difference between a permeability of 110, right? And definitely different than 102. So in small tubes, the space is limited for the cores, which limits the total magnetic capacity, which is the saturation flux density times the area of the cores. So proper design, SMCs can carry over double the 0.4 Tesla saturation flux density of typical ferrites under tube welding conditions. Yeah, we've tested a number of these over at Tesla in our lab. But if we look even at just 0.8 Tesla, our region of high process efficiency because the heat is then proportional to the impeder flux density squared. It's 4 times. We can really expand the area where we're operating efficiently. So why aren't all these impeders made of SMCs instead of ferrites? So there are advantages to an SMC. In tube welding, it's primarily that high saturation flux density, which leads to that performance improvement. Another nice feature is the temperature time stability. Ferrites are very temperature sensitive, their magnetic properties. SMCs have very stable magnetic properties over a fairly wide range until they destruct thermally. If you keep it below that temperature, the properties are very stable, which leads to improved stability of production. Yeah, the ferrite properties are very sensitive to that temperature and also mechanical stresses and vibration. The disadvantages of an SMC: cost of the impeder. These are more expensive. Ferrites are made in very low cost production in very large volumes. SMCs are a smaller volume production, custom machined, with more high value add materials. They have lower permeability at low fields, which is why they aren't for everywhere. As we said, if you're in that area that's not saturated, keep doing what you're doing. If you have no problems, keep doing what you're doing. It's when you get past those cases where you start to struggle, that's really where the SMCs come in. And they do have higher losses than ferrites. So these require us to think better about the cooling, not to keep the temperature of the core lower, but to keep it below that critical temperature where it starts to break down. Based on this, these likely aren't going to work in gas-cooled systems. So we do need water. Main opportunities we're seeing in the market currently: small diameter, heavy walled tube. These are generally where ferrite impeders struggle if they're return flow. Small tube applications where the welder is the bottleneck and the impeder is in saturation. So if your welder can't keep up, you can't turn the welder up enough, coils start blowing, there's a good chance an SMC impeder will help you. Applications where impeders frequently fail due to mechanical impact with the line. Again, we can make them smaller and still get better performance. Applications with metallic components inside of the impeder. These are critical. A lot of times the heating of those is what limits your ability to turn it up. And applications with very short impeder life. Here's another case story that we did in collaboration with Kent Corporation. They're one of the larger consumable supplier in the tube welding market. So for this case, it was about 400 kilohertz, 300 kilowatt power supply. It was a half-inch OD steel tube with a 1¼ millimeter wall thickness. This case, again, they were using 8.5 to 9 millimeter OD impeders, and that's the OD of the casing. The impeder core inside is actually much smaller. And the energy savings for the same line speed was about 20%, even though we used a smaller Fluxtrol A impeder compared to the ferrite impeder that was being used. And all metallurgical and structural tests passed. They were actually having a hard time meeting their weld requirements with the ferrite impeders. So even though the tube size and wall thickness is similar to the previous two studies, the energy savings is 13 kilowatts, or the equivalent of preventing 45 tons of CO2 per year and 5,200 annual electricity. Taking the time saved to produce the same amount of product, over 50 tons of CO2 could be prevented and 5,700 saved with increased production speeds. So that's another one where the line was running at 82 meters a minute. If you tried to go any faster, they had trouble. We were able to turn it up to 93 meters a minute, and there was no real reason we couldn't turn it up farther other than these tubes were being unloaded manually, and the operators couldn't unload the tubes fast enough. So we firmly believe that this could have got up to the speed of the machine, which is, I think, 110 meters a minute on this line, but we weren't able to turn it up enough because the operators couldn't unload the parts fast enough. So the other key feature was because that thermal instability of the ferrites, the operator is always chasing the process. They're always having to move that dial up or down, constantly to keep that weld with good quality. With the Fluxtrol, they didn't have to touch the dial for over a full shift. While that thing was running, they didn't have to touch the dial. The only time we touched the dial, we would turn it up when we wanted to turn it up, which was turn up the speed and the power. So even though we were running 15% faster, we were still using over 10% less power. The other key feature, no arcs and sparks, right? These weren't popping. With the ferrites, you're seeing a lot of sparks and arcs. Let's look at the value proposition for this one. And again, just keeping it simple, we'll use the same price for ferrite and SMC cores as we used before. They're kind of relative numbers. And here's what the impeder would be. We'll assume that it was 4 hours for the ferrite. That's being very generous based on what we know about production. And the SMC core, we watched it run for at least 12 hours. We don't know how long it ran, and there's no reason to believe that it wouldn't have been, kind of similar numbers to this, if not even better. So at those prices, you're again at a cost neutral. In this case, we'll compare the ferrite to the SMC that's actually running 13% faster. Even though we're running faster, we're using less kilowatt hours per ton and less power. So even though you're producing more tube per hour, you're still saving energy. If we look at the changeover times, same line cost range, this would probably be on the smaller end, just you're not producing as much steel. You see that same type of number, 300,000 to 1.8 million, somewhere in there, depending on what your costs are of your line. If we look at the scrap cost, tells the same story. Here again, because we're running faster, we get more hours on the line. We get a lot of additional production. So that production is the biggest of our costs. And I'm not double counting the downtime. I'm counting only the additional hours because we're running faster. And that's that opportunity cost. That's additional production value. So I don't call this production savings. I talk about total annual benefits because that's value add. If you can sell more product, if you have demand for more product, you can get that additional profit. So you're talking 800,000 to almost $5 million opportunity from making that change without a capital investment. So where are the barriers to adoption? Tesla 2 mil are expensive. It's 150 to 1,000 foot a minute line speeds are typical. Validation of new processes can be very expensive. So ferrites are proven technology and the current industry standard for decades. This is what we know. SMC cores are expensive. They're 10 to 50 times more expensive to purchase on an individual unit basis. This is the annual cost that purchasing looks at when they want to buy an impeder, right? But if you look at how many less you need per year, the numbers are often similar. And the production savings tend to dwarf any additional costs that you might have from paying more for the core, which is the least expensive part of the whole assembly. The main concern is really the SMC losses are higher. So we really need to focus in and have good cooling. Design good cooling circuits and design cores that can be cooled. So we need to be very mindful of that water circuit design. We started doing a validation approach at Fluxtrol. We use a combination of 2D and 3D models for the impeder cross-section design and the cooling requirements. Laboratory testing for welding impeder physical simulation. This is really a key component. So we're verifying these impeders are going to survive offline. We're typically running them for about 8 hours. to verify. And then we're providing field testing support with our industrial partners once the design is proven. So we're looking to be not an impeder supplier, but an impeder core supplier. We're looking to work with your current impeder suppliers and provide cores to them and have you have the same supply chain over time. All of this value add we're providing for free because we know our impeder cores work. And we want to de-risk them for you so you're comfortable to test. So how is our test cell designed? If we look back at our models that we showed earlier, the concern for us is not the overall loss in the impeder core usually. Mainly it's really, can we cool this area that's most heavily loaded? And that's typically kind of at the back third of the induction coil. But this is the normal distribution you get. How we simulate is that we made a simple coil that looks like a welding coil. And if we just take the tube out of there, right, because there's no way to cool the tube when it's running continuously for 8 hours without moving metal and producing tons of steel. So we just take out the tube. If you look, the flux density distribution looks pretty similar. You've got your high area flux density, and it falls off with distance from the source. And we put the impeder core in the impeder casing and run it with water continuously. And then we make sure it's going to survive. Prior to doing that, we've optimized the cross section of our core, right? We look at, okay, do we have enough total water, right? We have this many losses, kilowatts of loss or watts of loss in our core. So we need a certain amount of flow. Do we have enough space between the impeder casing, anything that's on the inside of the impeder, for the required volume of water to flow that's going to remove those calorimetric losses? So that's total heat removal. That's power is equal to mc sub p delta T. And then we run models where we look at the temperature distribution in the cross section of the core by applying a heat transfer coefficient. We're focused in on, can that area that's the highest magnetic loading, can that survive? And that's a convective calculation. So do we keep this maximum temperature in the core below our threshold condition? Now, as we get into more sophisticated impeders, this is a pretty simple through flow model. We're starting to look at using CFD models and understand how the water exits the supply line, how it fills the water cavity, and then how it flows on the exit, right? And whether that's return flow or not, but want to make sure the entire water circuit has the capacity to carry the amount of cooling that we need to remove the total loss and also those local losses. So this is something we're finding very important when we look at return flow impeders. And in those cases, a lot of times people haven't looked at the whole water circuit. They've just looked at a part. And that really has a huge impact on how much water flows there. Here is our current impeder test rig. And as we talked before, we've got an induction coil wrapped around. This is just a test holder that keeps our impeder and locates it. And we'll test these impeders either centered or intentionally we'll off-center them in some cases to kind of create a bias in magnetic field similar to you'll have in an actual line where a lot of the flux is being pushed through the weld seam. We have a supply and we have a drain, and we measure the flow rate and the temperature coming in and out of the core. And we measure the coil on the current and the voltage on the power supply. And we run these for hours and make sure that these are going to survive satisfactory in conditions that are more challenging than they'll actually be in the mill. Here's an example of a 10 millimeter solid fluted SMC core trial. In this case, you can see we ran 86-degree room temperature water supply, similar to what you get just off a mill, using mill water. We used regular water. Return water flow was about 96 degrees Fahrenheit. We had a pretty stable delta T of about 5.26 seconds. This initial ramp up is where we're in the bath, and then you can just see the closed loop cooling system regulating the temperature up and down. Ran this trial for 5.5 hours, 310 kilohertz. The flux density was about 0.8 Tesla for the long duration trial. Now, these are the predicted flux densities versus currents. So we measure the current. We plot those currents in amps versus the power loss that we measured based on the calorimetric data. And then we compare that to our FEA predictions. And we're generally getting quite good correlation. This gives us a high degree of confidence that our impeders are going to survive in the field and our calculations are accurate. To date in our lab, other than when we forgot to turn the water on, we have not failed a single impeder that we did not design intentionally to fail. So we have been designing some impeders intentionally to fail to find out really where are the limits of this? At what point does that impeder core start to break down? So we make sure that we're informed going forward about really what our capabilities are and making sure that these are bulletproof when they get to the mill for tests. Here's another case we ran in our lab. This was for a 10 millimeter hollow impeder core, and we tested these at 200 kilohertz, and we ran these at 1.2 Tesla. The other thing I talked about, stability of properties for SMCs compared to ferrites. Ferrites do have a lot of variability. There were actually here 5 different impeder cores tested, and there is the FEA analysis on them. And besides testing 5 different cores, we also tested 2 different designs. The only thing common about these designs is they had the exact same cross-sectional area. And you can see from the test both the current versus voltage measurements and the current versus power loss measurements. And compared to the FEA, these impeders are more or less indistinguishable from one another. So that just kind of proves our point, really. It's that product of cross-sectional area and permeability that really matters. Then it's just about designing that cross-section so we can keep the temperature in the satisfactory region. But we're getting very good correlation across the range. All of them aren't quite as good as this. We picked one of the better ones, but generally we're getting pretty high accuracy of calculation. In summary, many small tube welding installations are limited by the impeder. SMCs have the potential to greatly improve the performance of these installations. Savings are in the hundreds of thousands or possibly even millions annually per line. These savings come in the form of increased impeder and coil lifetime, production rate improvements if there isn't another bottleneck in the system, and generally we're seeing 20 to 50% energy savings / carbon reduction. SMCs have higher magnetic losses, so it is important to appropriately design the impeder core and cooling circuit, and we're happy to work with you to do that. Finally, we have a workflow for verifying the impeder capabilities offline based upon computer models and actual physical tests. So I'd just like to acknowledge multiple Fluxtrol team members who participate in the modeling, design, manufacturing, and testing of the cores. For the welding tests carried out at Prince & Company, GmbH, the impeder cores and the impeder system were manufactured by TW Tools. The project was financially supported by the German Federal Ministry for Economic Affairs and Climate Protection under the funding code ZF402804FH9. Grant participants, Technical University of Chemnitz, Professor Martin Kroll's group, University of Hanover, ETP, Dr. Nikonarov et al., Itron GmbH, our distributor in Germany, and TW Tools. And thank everyone for their attention today.